curve, and I ask you, well, which is the quickest way for a simple closed curve in the plane to collapse? Of course, the plane is simply connected, so you know that in some way you should be able to deform it to a point. Okay. Now the question is, what is the quickest way to do that? Meaning, the length of the curve gives you a functional over the space of curves. Okay. You can measure. I mean, this is a space where you can actually speak about the gradient flow. Okay. So at every point, you move by the gradient of the functional that you want to minimize. Okay? Well, this is actually the answer. So I just remind you, I just taught to the second line in class, but maybe, so for a curve in a plane, actually the only geometric invariant, metric geometric invariant is the curvature of the curve, which is denoted by K there, which is actually the rate of change. Once you parameterize the curve by arc length, you go and check the derivative of the tangent vector. This gives a vector, and you compute the norm of this vector. Okay? So the derivative of the tangent vector, so the way the tangent vector changes, gives you a special direction, which is called nu, but it also gives you some kind of modulus, which is called K, the curvature. Okay? And this is essentially the only invariant, metric invariant of a curve. So now what is this equation here? As I said, now you are introducing a time parameter. So you start with a curve, which is usually parameterized by a parameter that is called S. Typically, it's arc length. And now you move it in time. So that's at time 0. And time t, this is evolving via this law here. So every point is pushed in the direction of k nu, okay, at that speed, infinitesimal. This is called the curve shortening flow, because I said it's not difficult to check that this is actually the gradient flow of the length functional. Very interesting is this observation here. So you see, this looks like, instead of writing k and nu, remember, I just told you the definition of k and nu. So k and nu, try to write everything in terms of the original map x, which is actually the unknown of the problem. Okay? So the tangent vector is, of course, dx in ds. The secondary k nu is the second derivative with respect to the arc length parameter. So if you write everything in terms of x, this becomes the equation, the parabolic equation that you are studying. And this looks like a beautiful heat equation. You see, that's the key observation. So heat equations, every time you have a function of a given variable, y, you can actually deform this function via the heat equation by introducing a t parameter and then requiring that d in dt of the map x, y, t is actually equal to x, y, y, the Laplacian in general. Okay? This is the heat equation for the map. So this is nothing, so it's kind of interesting. So the length, the gradient functional, the gradient flow for the length functional is exactly the heat equation. Okay? This is a prototype, this is kind of a meta theorem. I'll comment that. So again, which are the solutions to this problem? Let's, a good way, and also, actually first, because once you know that something is the heat equation, the first thing you want, you are very happy usually because the heat equation is a linear equation. So then you take every book on partial differential equations, and at the beginning, the first 3 or 4 chapters are good for you. Okay, for this type of equation, this is a heat equation. You can throw the 3 chapters away. Why? It looks like a linear equation, a linear PDE, but it's not. Because every time the curve changes, the arc length changes. Okay? So here, S depends on X. Okay? So this is just a trick. It's an illusion. X is the map. I'm thinking of X as a map, for example, from S1 to R2. No. It's the whole map, sorry. No, it looks like the first coordinate of something. No, it's the whole map. But now you see every time, so for every t, so now I have a family, so I'm actually looking at x as a family from some interval, okay, 2R2. Now every time I fix t, I need to compute the arc length, and the arc length is nonlinear, okay? So here, this is just, as I said, it's an illusion of the way you write the equation, the linearity. So how bad really this equation is? Well, again, let's take the toy problem, which is, again, not exactly a toy problem. So suppose actually you are taking a graph. I mean, your initial curve is a graph of a function, and you want to know how does this graph evolve under curve shortening flow. Well, this is the answer. So here you see very well why this is a very nonlinear problem. Okay. Okay, actually here I tried to argue, I mean, I gave you some indication of the fact why this should be the length, I mean, the gradient flow for the length. But then, so of course, what are we asking now? So is it true that this flow actually exists? So typical thing in parabolic equation. This is a system, actually. It's a system of two equations because as Don was mentioned, of course, this has two components. Each of them must satisfy an equation. So this is a parabolic system. And what do you know? What would you like to do? Well, of course, you always try to prove short-time existence, long-time existence, convergence. Okay, these are the three steps in every. So short-time existence is okay, no problem. Long-time existence fails. And this is easy to see because if you take a circle of a given radius, this shrinks to a point in finite time. Okay? So there is a kind of a maximal time of existence, but still, you would like to know what does it happen to this curve when you are approaching the maximal time of existence for the flow. And the way, and this is actually extremely hard. The way people understood something about this is actually they noticed that there is a monotone quantity in this flow, which is actually given exactly, you see, by the length square of the curve at time t minus 4 pi the area inside. Okay? So if you compute the derivative of this quantity along the flow, you get that this is non-positive. Okay? This is actually easy, but then, well, easy but cute. I mean, so then out of this, so what is it really meaning? I mean, and then actually there was the hard part of the story, which was proved in 1987. So we are really at our time. That actually this quantity is not, I mean, on one side you know it's monotone. But on the other side, you know that it goes to 0 as t approaches the maximal time. So now you need a little bit of geometric intuition. What does it mean that this quantity is going to 0? Well, you see, the length square minus the area inside is going to 0. So for example, an evolution like this cannot happen. You see, you cannot collapse the area inside by keeping some kind of perimeter. So if the area inside goes to 0, also the perimeter must go to 0. This is why this statement is amazing. Okay? I don't know, is it clear? I mean, I'm happy to. You see, a geometric interpretation of this limit. Okay, so for example, this thing cannot happen. So your curve cannot shrink to a segment, for example. So where does it go? This is actually what is usually called in these things ruling out singularities of the flow. So then out of this, Gage Hamilton and Grayson, I mean, one for convex initial data and then Grayson in general, they managed to prove that actually this flow exists, of course, up to maximal time, and suitably rescaled, the limit of the curve, when you approach maximal time, becomes a circle. So of course, curves disappear. I mean, we constructed this flow to make curves disappear to somewhere, okay? The length must go to 0. So eventually, you will get a point. The interesting question is how you get a point. So you need to, once the curve is around this point doing some mess, you have to take a length, rescale, and see how is it going to a point, okay? If you do it properly, what they proved is that actually this becomes more and more the round circle, okay, of radius 1. Now this is fantastic, okay? If you like differential geometry and geometric analysis, this is a fantastic theorem. It's kind of curious the fact that you had to wait 1990 to see this. And actually, why you had to wait 1990? Because, of course, Hamilton was so frustrated by the Ricci flow. They said, look, let's play the easiest game. So the Ricci flow, for whoever knows what I'm talking about, is exactly, it's a very close variation of this idea for curvature in dimension, in any dimension, okay? So when he could not prove any theorem, in fact, he could not rule out singularities of the Ricci flow, he said, but how is it possible? Let's go back to the simplest case. And so in this sense, this is the simplest case of the Ricci flow, okay, of geometric evolution, or the mean curvature flow, which was actually already existing, okay? As for the isoperimetric problem, you can extract out of this theorem immediately also the isoperimetric inequality. This is yet another proof of the isoperimetric inequality, because you see this problem forgets about the area inside, okay? Actually, it's changing the perimeter, it's changing the area, everything. But of course, you can rescale every time. For example, you can prescribe the length of the curve to stay fixed. So you are doing something funny, because you are taking a curve shortening flow, rescaled in order to keep it of given length. Okay, so this is kind of unnatural, but it's interesting just to observe that in this way, Grayson theorem becomes the isoperimetric inequality. So I think this is actually the best proof of the isoperimetric inequality. Actually, I should have said already, I'm borrowing pictures and text from everywhere, okay? No, so sometimes I remember to say where, but okay, now I forgot. Oh, no, it's more than a book. It's an amazing proof. It's an extremely complicated proof. No. There is actually a 400 pages book, which is called the Curve Shortening Flow, which contains only one theorem. No, it's an extremely sophisticated proof. Because actually, you see, the problem you have to imagine is you have to rule out all possible ways singularities can occur. So if you think in higher dimension, and if I manage to save some time, I will say something. Actually, in higher dimensions, singularities do occur. Okay? So it's quite amazing that actually they don't here. And there are many ways. Actually, we are happy to have with us a great expert, who is not here, but so this seminar serves also as an advertisement for a series of seminars that is starting in 10 days in geometric analysis. So Niels Möller, a fresh colleague of ours, for example, he's a great expert of singularities of higher dimensional versions of this. Anyway, I prepared also another thing. So this link I put there, it's kind of fun, but now maybe I'm getting a bit slow. There is actually a mathematician who had fun creating a beautiful simulation, computer simulation of the curve shortening flow, where you can actually go there and with your mouse draw the curve you like. And actually, it's amazing. And you will see the evolution, okay? The evolution in time. So actually, I suggest you, which is people, experts in the field, know that this is the nightmare of the flow. So if you want to know, if you want to check whether this guy was good and the program is good, draw this. Actually, maybe just one comment. Why this should be the nightmare? I mean, this is not just fun, okay? You see, evolving by curvature means that this point will start extremely fast in this direction. Boom. Evolving by curvature will tell you that this point will go extremely slow in this direction. This is almost flat. This is extremely curved. Okay? So who wins? Who does it win? Who does win, or whatever? Okay, the amazing curvature here, or the empty curvature here? So, and actually, this is the hardest part of the theorem. They even, nobody wins. So this just becomes, they flow. So you will see the evolution of this curve is that this snake unrolls and becomes more and more round and round and round, and then eventually it will be round. Okay? So there is kind of a compensation phenomenon between these two things, which is amazing. And in fact, actually now, look, I think I will start improvise because I think I've prepared a 3-hour seminar. So let me show you. And in fact, you're a bit too silent. You should be free to ask things. Let me show you why people have been, you see? Okay, so this was about, so this would be a second hour of the seminar. So let's play the two-dimensional game. So let's flow by curvature a surface now. Instead of flowing a curve in the plane, let's flow a surface by curvature. Now, unfortunately, I was spending 3 or 4 slides to explain what it means by curvature for a surface, because a surface now has many curvatures. It has the Gauss curvature, the mean curvature, and so on. The right thing to do is the mean curvature, whatever it means. And actually, these are, for example, computer simulations of mean curvature flow. This is exactly the same thing. It's the heat equation played with, okay? But now, unfortunately, fortunately, in some sense, mathematics is interesting because it's difficult. Every type of singularity is allowed. Things can collapse to a segment. So a surface could become a segment. Necks can disappear, can pinch. So this was exactly what I was trying to convince you that here was not happening. So a neck, a one-dimensional neck does not disappear. A two-dimensional neck disappears. So a connected surface could become disconnected just by pinching in between. Okay?
Just a question. In the two-dimensional setting, when you flow it this way, can you not start self-intersecting?
Excellent question, because back to...
Can you repeat it?
So the question is, since I hope I said, I'm starting from an embedded curve, so nice without self-intersection. So one crucial property that you have to prove is that actually this embeddedness property stays along the flow, okay? And this is highly non-trivial, okay? So in fact, you can prove even more. The curve shortening flow has this other nice thing. If you start with 2 curves that don't intersect at time 0 and you flow them, they will never touch. I don't know where they will go, but there will never be a time where, okay. But actually answering your question, because as I said, I mean, one of the hidden messages behind this is how to choose a good problem. Well, how to choose a good problem? Unfortunately, if this is a really good problem, if I knew any idea of how to solve it, I would do it myself. But what about the curve shortening flow for non-embedded curves? So what about if you start from something like this? I mean, it makes perfectly sense to flow the gradient flow by length, okay? The length gradient flow of this curve. Nobody knows what happens in general, of course. Maybe for that one we can play some game and we will find out, but there is no general theorem. You see, in principle, this can also disconnect, or I don't know. And even more difficult is what happens in R3. So suppose you take a closed loop in R3 and flow by curvature. Well, maybe there the guess is still that it becomes some kind of a planar. Now it's non-planar. Maybe in time it becomes a planar circle. Nobody knows how to prove it. Because actually they have examples for both of these things where singularities can happen. So this almost contains the same amount of difficulty as the proof of the Poincaré conjecture. Okay. If you start from an embedded, for the 3-dimensional thing.
The theorem says
if you start with an embedded closed curve in the plane, you get a circle in this funny sense. Remember, you will always get a point. So if you strictly speak about the limit is a point. The problem is, what if you rescale everything before it becomes a point and see the limit of the rescale thing? And the theorem says it approaches. I mean, now you can speak about the limit, and actually this limit is the circle. Okay?
This is only in the plane.
Only in the plane and only for embedded. Okay. Now, where was I? Okay, honeycombs were gone. Curvature flow. So, okay, about this, I mean, if you want to play on this website, it's actually fun. Because, I mean, it's one of those questions you think it cannot be true. So you really challenge the flow with your most horrible curve. And actually, the flow always wins. So it's... Now, just another important historical comment, but not just historical. There are very simple proofs, and historical, these are all the proofs that were known for almost 2,000 years about the isoperimetric problem, which actually the main argument is like the one I outlined there. So if you start from something which is not the circle, then there is actually a procedure which makes it, for which you can, the output of the procedure is to enclose more area than before. So now the question is this a proof? See, we are trying to prove, so the statement is, the circle is the one which has the maximal area inside. Okay, for 2,000 years, there were about 30 proofs of this type of statements. Okay, so actually this hits one of the most delicate points in the calculus of variations, unfortunately for everybody, but I mean, there is actually Perron, a very important mathematician of the beginning of the 20th century, when actually criticizing a colleague for giving yet another proof of this type. Since the colleague was a geometer, he was an analyst, of course, he was claiming that geometers are not able to write down proofs, correct proofs. And he said, well, the argument you gave, the poor guy was called Steiner, which actually was a very smart guy, but I mean, he passed into history for this mistake. Okay, so what Perron wrote, actually this is taken, I mean, translated from the German, but it's actually taken from Perron's paper. Okay, it's not very nice to have such a comment written on paper. Anyway, so theorem, among of curves of a given length, the circle encloses the greatest area. Proof by Steiner. For any curve that is not the circle, there is a method, symmetrization, reflections, blah, blah, blah. By one finds a curve that encloses greater area. Therefore, the closest, the greatest area. So he said, look, geometers don't know really logic, because in the same way, I can prove that among all positive integers, the integer 1 is the largest. Proof. There is a method that if you give me any number different from 1, I create a bigger number, square. So 1 is the biggest number. Okay. That's one of those very, I mean, it's fun now, after 100, actually it's exactly 100 years old. It must be very tough to receive this kind of comment when you are alive, because actually it's true. I mean, he did this mistake. I mean, actually many people did this mistake for 2,000 years. So what's the problem here? The problem is that nobody realized that before proving that the solution is the circle, you need to prove that your problem has a solution. Okay? You see, that's what is missing here. I mean, this proof is correct, except the problem has no solution. Okay? So that's the moral that Perron was trying to advertise to everybody. And actually, there is another famous example of this occurrence, and now I fight back. I feel like I'm a geometer, so let me mention a mistake done by an analyst of the same type, which was another of these very famous, you see, we have lost a little bit touch with practical problems, at least well, that's what I feel. I mean, in the 18th century, mathematics was really much more related to everyday life, and one of actually a very popular problem was the problem of describing the shape of the perfect column, of the most solid column. Okay? So for thousands of years, columns have been designed in this form. This is actually taken from a 16th century book, but because this is based on Apollonius' rules, which were driven only by aesthetics. Okay, so the point here is that if you are more or less tall like this point, and you stand below the column, you will see the column will look for you like a cylinder. It's an optical thing, and it was just an aesthetic problem. Then, of course, the Bernoullis, Euler, Lagrange, I mean, okay, but now you know what some elasticity theory, something you can speak about solidity of a column. So what is the most solid column that you can... And then Lagrange wrote a famous paper where he proved that the most solid column is the cylinder. And this is not true, because he assumed that the solution existed in his space of functions. So he restricted himself to study this variation. This is a variational problem. Now, I don't write for you the law of solidity of a column, but I mean, he assumed the existence of a solution among smooth functions. It's actually easy to prove it has to be rotational invariant. Okay, so it's really a one-dimensional problem. It's a problem about a curve. So he assumed the existence of a smooth solution, and then among smooth solutions, the straight line, the horizontal line that then you rotate becomes a cylinder is actually the solution. Then people realized 20 years ago that this was actually the mistake done by Lagrange, and actually, for your curiosity, if you want to know which is the most solid column, it is this one. And you see why, I mean, the point is that this solution must have singularities. If you continue this column a little bit, I mean, here they have put something in between which destroys the whole point of the picture, but I mean, the whole point of the picture is that the solution will look like this. It has a singularity there. Okay, this was just a curiosity, but then unfortunately I cannot give you any idea of how to solve. Now you know there is a problem. You give me a variational problem, geometrical or not. First you need to prove that the solution exists, and then you can start analyzing the possible solution. Now, how in the isoperimetric world and in all these type of things, geometrical problem, unfortunately it's too complicated to tell you in a basic notion seminar how people have solve this problem. So basically, it was the birth of a subject which is huge. It's beautiful. It's called geometric measure theory. And basically, the idea is you enlarge so much the space of competitors, you define something that are usually called locally integral currents or rectifiable currents and so on. You prove existence in this space. Actually, the three giants are here, Almgren, Federer, and De Giorgi, in the 50s and 60s, essentially. They developed all this theory. And then the problem becomes, so you see, in order to get the solution, you have decided to take into account very rarefied things. So curves will not be curves anymore in your intuitive sense. Surfaces will not be surfaces, and so on. So then, once you have such a solution, you need to prove regularity theorems. Okay? So you need to go back from your monsters to real life. Okay? But this is one advantage is that usually these existence theorems for these kind of monsters are kind of typically, I mean, I know very few places where actually the dimension of the space that you are studying is actually important. I mean, but actually from there to the regularity, the dimension is crucial. So, okay, so here I was trying to describe to you what is the mean curvature of a surface, what is actually the curvature of a surface. Now it's not that obvious like the derivative of the tangent vector. Now you have a plane. Now you would like to speak about the curvature as the derivative of the tangent plane, but what does it mean to take the derivative of a plane? So you pick, essentially, what you can do is that you pick two vectors in this plane, and for each of them you measure the individual curvature of the corresponding curves, but then you have this indeterminacy about how did you choose these two vectors. So actually, none of this curvature is interesting. The two interesting things that you can do is actually taking the product of these two or the average of these two. So if you take the product of these two, you get